We're going to continue on in chapter one with this abstract idea of problem solving. We want to really figure out how will students be able to understand and explain finding patterns and determining if that pattern actually holds out in the long term. We want to look at deductive and inductive reasoning and when to use them. And then we're going to look at a few example types of sequences. So, really, in chapter one, we're trying to teach how to think. So, it is going to be a very abstract process as you work through the lab in homework one. We also want to teach them how to find the nth term if a pattern does continue, and how to use differences to find if a pattern is neither arithmetic nor geometric. So if I start to look at patterns, I notice that as I add these numbers together, I am getting a pattern of 1, 11, 111, and so on. So how can I describe this as a pattern? The thing about patterns is there's not always one way to look at it. For example, the numbers on the left are going to be natural numbers on the far left, and the patterns are going to start with 1 and continue with the next greater natural number in the line. So I had 1 plus 0, 2 plus 1, 3 plus 1, 2, 4 plus 1, 2, 3. So I'm looking at that next greatest number. Depending on how I think, I may see that slightly differently. The numbers in the middle could also be seen as the products of the two numbers, the second side of which is 9. So the first number has a product of 0, the second number has a product of 9, and so on in succession. The resulting numbers on the right are going to be formed using ones and have one additional 1 in each successive line. So those are all different patterns that I can get from looking at this one image. Do the patterns continue? Why or why not? Well, if I want to see if it continues, it might be good to skip ahead 6 or 7 steps and let's see if it holds. Because I don't want to do every single step. I want to go ahead and get something really out there. And what I find is it does not continue because what's on the right side is not all ones. So the pattern does break down at some point between where we were on the previous screen and where we are on the current screen. So I want to use my inductive reasoning to make a generalization based on that observation. That may lead to something called a conjecture. So students typically understand the word hypothesis better than conjecture, so you might want to make that connection for the students. A statement that is thought to be true, but is not yet proved. So it's very similar to the idea of a hypothesis in a science classroom. Now, in math, we play the devil's advocate a lot. We can prove something as false by giving a counterexample, and that is how we actually work on proofs at the lower levels. So I'm just looking for a contradiction, just like we just did. I took it way out there and I found that it broke down. So there was a contradiction, so it conflicted with that previous pattern. Now, the danger of making conjectures is that they're not proven to be true, and you might could spend all day trying to prove something to not be true. So in this figure, I have 2 points that determine 2 regions, 3 that divide it into 3 regions, and so on and so forth. What's the maximum number of regions that could be found by using 10 points? Well, it appears that each time we're increasing the number of points by 1, we double the number of regions. If we base our conjecture on that pattern, we might believe that 10 points, we would have 2 to the ninth or 512 regions. An initial check for this conjecture might be to see whether we get 16 regions for 5 points. For 6 points, the pattern predicts I'll have 32, and there were actually 31. So in this case, to jump, 7 or 8 steps ahead, that's a really complicated figure. So I might just want to go 5 and 6 because these are growing exponentially. They're much more difficult to jump 10 or 8 steps in the future. Now, a sequence is going to be an ordered arrangement of numbers, figures, or objects. Sequences a lot of times are thought of as patterns. Sequences can be classified by their property. In a sequence where each term is found by adding or subtracting the exact same value every time, it's called an arithmetic sequence. So the sequence 2, 5, 8, 11, 14, dot, 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 is arithmetic because each time I'm adding the same value of 3. If I'm adding different values, it's not arithmetic. It has to be the exact same value. Here's an example. If I want to find the pattern and the number of matchsticks required to continue the pattern, I'm going to note that the addition of a square to the arrangement requires adding 3 matchsticks each time to form the 3 sides of the rectangle because they share a side. So it's already sharing one side, so I only need 3 matchsticks. So thus, if I wrote it as a pattern, I would have 4, 7, 10, 13, where it's an arithmetic sequence. Now, what if I give you the first 4 terms of a sequence that seems to be arithmetic? Well, if I have 7, 11, 15, and 19, the sequence seems arithmetic with a difference of 4. So to find the first 4 terms of a sequence given by this and determine whether it seems to be arithmetic, I would plug in my term numbers, which always starts with 1. So I'm 1 squared minus 1, 2 squared minus 1, 3 squared minus 1. And I see if I look at these numbers that I get from this, from 0 to 3, I add 3. And from 3 to 8, I add 5. So right there, it's not going to be arithmetic because you can't add 3, then add 5. You have to add the same number every single time. So this is not going to be arithmetic. The diagrams in the figure show the molecular structure of an alkaline and a class of hydrocarbons. This is just a different visual example of what is happening in a pattern. Each time I'm adding a carbon, and that carbon has to be paired with your hydrogen atoms. Heptane is an alkaline with 100 carbon atoms. How many hydrogen atoms does it have? So if we start looking back at the drawing on the previous slide, and we disregard the extreme left and right hydrogen examples in each, if we look at this, we see that for every carbon atom, there are 2 hydrogens. So therefore, there are twice as many hydrogens as carbons because I have 2-to-1 ratio. So if I want to summarize this, I can start looking at this as if I have 2, I have 4, but then I still have those 2 extras hanging out, which is 6. If I have 3, then I have 6 because I'm doing 2 times 3, but I still have the 2 on the end that I have to account for that were extraneous. So my pattern is 2n plus 2. Here is another example. A theater is set up in such a way that there are 20 seats in the first row and 4 additional seats in each consecutive row. The last row has 144 seats. How many rows are there in the theater? So my starting row is 20. My ending figure is 144. I'm adding 4 seats each time because there's 4 additional seats, so that when I plug in this value and I look, I get 32 equals n because I'm going to take 20 plus n minus 1 times 4. I'm going to subtract 20 to get 124 over here. I'm going to divide by 4, and then I'm going to add 1. So that's the process you're following with that linear equation. Here are some specific sequences. The Fibonacci sequence, it starts with 1, 1. As soon as I see 1, 1, I start thinking that I probably have something that's going to be a Fibonacci. If I want a sequence in which something is successive by obtaining the previous term from multiplying, that's going to be a geometric, but I have to multiply by the same number every time. So in this case, this would be geometric because I have a to the n because exponents are repeated multiplication. So if I look at this pattern, 1, 3, 6, 10, and I look at 1, 4, 9, 16, these are figure 8 numbers because they're sequences of numbers represented by dots, and then they're being arranged into geometric figures. Here, you might think, well, I just multiply by 3, but we see that actually does break down here with 6. Here, same thing. I'm not adding 3. I'm not multiplying by 3. So these are neither geometric nor arithmetic. If I want to use differences to find the pattern, then I can assume that a pattern might continue. So this would be when something is neither geometric nor arithmetic, you can look at what the differences are between each number to see if maybe there's a pattern to what you're adding or subtracting. And you can continue that pattern until you get a difference that's the same. So now that I look at this, I say, oh, I'm adding 7 each time down here. So that will allow me to generate the next term, which is 116.